Well, so far we've looked at central angles and the measure of the related arc, and inscribed angles and their measure of that related arc. Today we're going to kind of expand our universe a bit, and as I talked about a couple days ago on the podcast, start moving that point of intersection around a little bit. Now, there are a couple theorems that come up here that really aren't presenting anything new. They're just special cases, so we don't get too excited about them, but it's still useful. Theorem 10.4 talks about what happens when a tangent intersects a chord instead of two chords, what's going on. Well, essentially, if I look at this picture, and I'll expand it a little bit, okay? When I look at the picture here, the point A, the point of intersection, is on the circle, isn't it? Which, even though technically this is not an inscribed angle, we use the same rule as an inscribed angle, where an inscribed angle has a vertex on the circle like we see here. So when that vertex is on the circle, whether it's two chords causing that or a chord and a tangent, we still do the same thing. The measure of the angle is half the measure of the arc. Now, in this case, we actually have two different angles and two different arcs, and it would make sense that, we know that the measure of angle 1 plus the measure of angle 2 is 180, and the measure of arc AB plus the measure of arc ACB equals what? Well, that's a whole circle. That's 360. And the sum of the angles has to be half the sum of the arcs, and the measure of each individual angle is half the measure of each individual arc. So that makes sense. We still get that double half relationship. So if they say, for example, angle 1, they love to give you questions like this. Angle 1 is, say, 80 degrees. Find the measure of arc ACB. So they ask you for the opposite arc instead of the arc that's caused by that angle. But that's not so hard because, well, if 1 is 80, 2 has to be 100 because they're supplementary. So that arc is 200. Or we could say if 1 is 80, this arc BA is 160. ACB, that's right. Arc AB is 160, which means 200 degrees left for the arc for ACB. So a couple different ways of looking at it. It's not earth-shattering. It's really the same thing we've been doing before all along with inscribed angle. Vertex on the circle, angle is half the measure of the intercepted arc. And very basically, just a little practice here, this arc is 130, angle 1, and you really can't go the wrong way here. If you doubled the arc and got 260 for the angle, that wouldn't even make sense. So half of 130 is 65 degrees. Same here, it wants the red arc. It wouldn't make sense to go half this time. We know it's a double half relationship. Going half would be, 62.5 degrees for that arc, which clearly is not correct. We double it to 250 degrees for the arc. All right. Now the more interesting stuff. When I have two secants intersecting a circle, they can intersect a couple different ways. We can intersect on the circle. That's inscribed angle. We've covered that now. But they could intersect inside the circle. So we could see this situation where the intersection is inside the circle but not at the center. Or we could have that point of intersection be outside the circle somewhere. And inside and outside are what we're going to be interested in now. What happens when it intersects inside? What happens when it intersects outside? Inside the circle and outside circle have very similar formulas. They actually only differ by a sign. But the key idea here is that both times these happen, we're not just going to get one arc, but we're going to get two arcs that's intersected by that situation. So here angle 1 has a vertical angle, and the angles intersects two different arcs. Now those arcs are very clearly different. In fact, I could probably see that better on a slightly larger picture. So let's go ahead and make a nice large circle. And I'm going to have one here and one here. Okay, there are my two chords. I'm going to call this angle 1 and angle 2. Now, it's obvious that the measure of the angle can't equal the measure of the arc or half the angle of arc or double it, because those angles have to be congruent. Angle 1 and angle 2 have to be congruent. They're vertical angles. Clearly, the arcs are nowhere near congruent. Okay? So I know the measure of angle 1 can't be related just to the measure of, we'll call this arc 1 out here. I'm going to call this arc 2. So the measure of angle 1 is not related to arc 1. The measure of angle 2 is not related to arc 2. But, interestingly enough, if I take the sum of these two angles, it happens to equal the sum of the arcs. Oops. Put the arc in the wrong spot there. So individually, each angle is not the same or even related to the measure of the individual arc it intercepts, but the sum of the vertical angles equals the sum of the arcs. Now, that's pretty interesting in and of itself. But we know the measure of angle 1 equals the measure of angle 2, right? Because they're vertical angles, these two are congruent. So I could say 2 times the measure of angle 1, because that's the same as measure of angle 1 plus measure of angle 2, equals the measure of arc 1 plus the measure of arc 2. Or I could say the measure of angle 1 is 1/2 times the measure of arc 1 plus the measure of arc 2. And that's the formula the book gives us on the previous page. Okay? That the sum of the angles is the sum of the arcs, so the measure of any one angle is half the sum of the two arcs. Now, quite honestly, most people, instead of doing that, this formula down here, most people just remember this part right here, that the sum of the angles is the same as the sum of the arcs. And you just got to remember that the two angles have the same measurement. The arcs do not have the same measurement. That is obvious. Okay? So that's what happens when you have vertex in the circle that is not at the center. Next case is what happens when I have two angles that are in the circle, or that are not, two arcs that are intercepted with an angle outside the circle. Okay? And it doesn't matter if they're intersecting here. We can see in the picture, whoops, don't want to do that necessarily. Okay, we've got 3 different cases. I could have 2 secants. I could have a secant and a tangent, or I could have 2 tangents. Okay, there's my 2 tangents. There's my secant and a tangent. There's 2 secants. In either case, the point of intersection is outside the circle, and in either case, the formula is exactly the same. Where when the vertex is inside, we add the angles and divide by 2. When the vertex is outside, the difference in the formula as we change it from adding the angles is we subtract the angles, always the bigger, or subtract the arcs, and divide by 2. And it's always the bigger arc minus the smaller arc, by the way, because the angle has to be a positive measure. We want to keep it that way. So it's big arc minus small arc divided by 2 equals angle. So again, maybe a little picture of that. Circle. I'm going to draw it. It doesn't matter if it's a secant and a tangent or 2 secants or whatever it is. I'm going to draw it as a secant and a tangent. Again, big arc, small arc. So I'll call this arc 1. That's awkward to put that in green if I highlighted it. I'll make it red. Call this arc 1. We'll call this arc 2. We'll call this angle x. And the measure of angle x equals 1/2 the difference of the arcs. Bigger arc minus smaller arc. Difference. We subtract the arcs and divide by 2 to find the measure of the angle. So when the vertex is inside, the measure of the angle is half the sum of the arcs. It's a plus sign. When it's outside, it's half the difference of the arcs. So essentially the same formula, it's just differing by a sign, plus or minus. Let's apply it. Here I have an angle I'm looking for, and I have the two arcs. So let's see if I can expand this picture a little bit. Whoa, okay, that was fun. All right. So this one, I have my formula, the measure of the angle equals 1/2 the sum of the arcs intercepted. So this angle intercepts this arc. The vertical angle here intercepts this arc. These two angles are the same. These two arcs are not, but I take the 130 plus 156 and divide it by 2. So it's 1/2 286 or 143. The other way we looked at it, we talked about it, said the sum of the angles is the sum of the arcs. So I could have, instead of writing it this way, I could have said x plus x equals 130 plus 156. So 2x equals 286. Divide by 2, and guess what? We have exactly the same situation. It's the same formula. So again, either angle plus angle equals arc plus arc inside, or sum of the angle is, or the measure of the angle is half the sum of the arcs. For an exterior angle, we use essentially the same formula, but we change this from a sum to a difference. We got to do bigger minus smaller. So I'm going to let you try B on your own. A circumscribed angle is just a special case of this. This is nothing really that exciting. The only thing we have to realize is that my two arcs, whatever the two arcs are, they're always going to add up to 360. Because together the two arcs make up the entire circle. So if I call this x, then this arc has to be 360 minus x. Or vice versa. If I call the small one x, then it's 360 minus x the other way. Okay? And we have a theorem that helps us with this. It says the measure of a circumscribed angle is equal to 180 degrees minus the measure of the central angle that intercepts the same arc. Okay? So the measure of this angle, ADB, is 180 the measure minus the measure of this angle, the angle that makes the central arc. So we know that the measure of ACB is the same as the measure of arc AB because it's a central angle. And we get this little theorem. It's a shortcut. You really don't have to know it very often. You can usually figure it out without memorizing the theorem. So let's take a look at that. It says find the value of x. So what do? Well, I need to find the measure of the arcs. Excuse me, I'm going to sneeze. Sorry about that, and it can be noisy in the podcast. So I look at this first situation, I say, what information I'm given? Well, I need to find the measure of this angle. The measure of that angle is going to be 1/2 the difference of arc 1 and arc 2, right? That's my formula. I'm going to subtract half the difference. That's the measure of my angle. Well, this arc has to be the same as the measure of this angle because that's a central angle, so that's 135. But I don't know the measure of this arc, or do I? I can figure that out because the two arcs together make up a whole circle, 360. So this arc has to be 360. Take away the 135 that's already used, that's 225. And there's my whole formula set up. 225 minus 135 is 90, or 45 degrees. The other thing we could have done there is we could have used that little theorem. It says the measure of the angle is 180 minus the measure of the central angle that intercepts the arc. And sure enough, we've just kind of confirmed that the measure of this is 180 minus the 135. Now, the reason I don't put a lot of stock in that theorem is because that's a pretty special case. We don't run into it very often. And quite honestly, if I know that, I know enough to use my formula And I can just dive right in. I'm going to get you started on number B, which is your final question of the day, because we know our formula, the measure of the angle equals 1/2 the difference in the arcs. Big arc minus small arc. But I've got a little work to do here, because all I have is an inscribed angle as my x. So let's think about this for a second. If this angle is x, then the measure of this arc has to be, 2x, twice as much. So that's my small arc. If that arc is 2x, how long is the big arc? Well, it has to be 360 minus 2x. And from there, I'm going to let you complete the algebra. So I've pretty much set it up for you. One final example today, and it's kind of an application. The northern lights are bright flashes between 50 and 200 miles above the Earth's surface. A flash occurs 150 miles above Earth at point C. What is the measure of arc BD, the portion of the Earth from which the flash is visible? The Earth's radius is approximately 4,000 miles. Okay? So again, what we have to do here is we're going to try to find the measure of this arc running across here, given the information that we're given. Now, this is a tricky little problem because we got to try to figure out what that angle is given the given very limited information. So when I look at this, what do I know? Well, I know that CD is a tangent here, which means that that's the right angle. And so I could set up Pythagorean theorem to find the length of CD very quickly, because CD squared plus 4,000 squared equals 4,150 squared. Now, that's some big numbers, but I have calculators for that. 4,150 squared minus 4,000 squared. And take the square root of that answer. And that's 1,106 approximately. It's 1,106 miles. So now I've got a triangle that has sides at 4,000, 4,150, and 1,106. Now, what I really need, I've got an arc in here. This is a central angle. How could I go ahead about finding this angle? Oh, trig. That's right. I have trig functions. And what do I know if this is my perspective? And I know 4,150 and 400. Well, 4,150, that's my hypotenuse. And 4,000, that's my adjacent. This is my opposite. And to solve for an unknown angle, I just set up a proportion. Now, I can choose, because I know all three sides, sine, cosine, or tangent. Let's go ahead and use cosine, because that uses the given numbers of 4,000 and 4,150. So cosine of my angle, which I'll call x for now, equals adjacent over hypotenuse. And if you recall, the way we solve that, when the angle is unknown, we use the inverse function. And then we can just put that in our calculator. Cosine inverse 4,000 divided by 4,150 gives me 15.5 degrees. So that means that this whole angle, because it has to be the same, that angle has to be 2 times that, or 31 degrees. So this arc on the Earth is 31 out of 360 degrees, or about 1/10, well, 1/12 of the planet can probably see that. 31 over 360 is approximately 1/12. So that can be seen for 31 degrees for a 150-mile flash. Okay, that's pretty tough. We have to bring in some trig. It's a good review because, hey, exams are coming, and you're going to have to remember how to do that. It's kind of a longer podcast. Apologize for that, but we'll see you in class.